the session is planned as follows, that is, we will make a beginning by talking about the chemical synthesis of alpha amino acids. Herein we will try to put the synthetic methods in two groups. First we will talk about the general methods, and then thereafter we will take up one example of a enantioselective method of synthesizing alpha amino acids. Having done that, we will move on to the reactions of alpha amino acids. Here again we will put into two groups. First we will discuss the reactions which are important for identification of alpha amino acids, and then we will talk about certain reactions which are useful for the peptide synthesis part, which we will be taking up in the next session. And towards the end we will try to sum up what we do in today's session. Okay. Now, let us make a beginning by starting with the general methods of synthesizing alpha amino acids. There are a number of methods available to synthesize alpha amino acids, but the important ones are as follows. That is, the first one we will be taking up is reductive amination of aldehydes and ketones. The second one is amination of alpha halo acids. The third one is Gabriel Malonic ester synthesis method, and the fourth one is Strecker synthesis. So, there are four methods which are used very often nowadays to synthesize alpha amino acids. We will take up these one by one. Okay. Now, reductive amination of aldehydes and ketones, as the name suggests. So, this is actually one of the best methods of synthesizing amines in principle, but that actually is made use of in synthesizing alpha amino acids. And the method is as follows. It is a two-step reaction, wherein in the first step what we do is we take an alpha keto acid and treat it with excess of ammonia. So, with this reaction what we get is an amine. That means, you start with an alpha keto acid, this is my acid group there, this is my alpha keto. So, if we take an alpha keto acid, react with excess of ammonia, I get an amine. And in the second step, this amine is reduced with the help of a hydrogen in presence of a palladium catalyst. And the reaction is as follows, that is, this amine gets reduced to amine, and what I get is my alpha amino acid. So, very simple method to do that. Now, the method actually is called as reductive amination, because we are first doing amination and then trying to reduce the thing. The importance or the significance of this method is that though there are two steps in that, but this method can be done in one step, because what we can do is we can in one pot we can take the keto acid, take ammonia, and also add the hydrogen and palladium there. In one step we can get product in one go. So, that is one method which we make use of in synthesizing alpha amino acids. We can take an example here. The example we can take it of, say it is 3-phenyl 2-oxo-propanoic acid. So, that is my starting compound here. So, this I am just taking the first step is reacting with ammonia, and then there is a reduction part with hydrogen and palladium. So, what I get is I get DL phenylalanine, and this will come out as an ammonium salt here, because that will be CO minus and NH4 plus. I can just recover my acid from there. So, what we see here is this method is very simple and straightforward, but what I am getting is I am getting a racemic product here. I get a DL mixture here, and the yield is not very good, but method is very simple. Okay. So, that is my first method of synthesizing alpha amino acids. Let us pick up the second method. Second method, as I mentioned earlier, is amination of alpha halo acids. In this method, this basically, as the name suggests, it involves amination of alpha halo acids with excess of ammonia, and it's also referred to as a direct ammonolysis method. What basically we do is we take an alpha halo acid. So, I am sure that we are able to gauge here that our strategy is we start with some kind of a grouping in the alpha position, and then we try to introduce our amino group over there. So, we start with the carboxylic acid, and then we try to introduce an amino group in the alpha position there. So, in this method what we have is we have alpha halo acid, we treat it with excess of ammonia. As a result of that, what we get is an alpha amino acids. It is a one step reaction here. The alpha halo acid actually is made by using H with Z reaction, which I am sure that you are familiar with this reaction. In this reaction what we do is we take an alpha oxo acid and convert that into an halo acid there. This is a very simple method which you are familiar with. Now, let us take an example. We try to take an example here. and see that how do I get alpha amino acid by using this method, amination of halo acids. So, the example here is of I take a starting compound to be 2-bromo 3-methyl pentanoic acid. So, essentially I have acid group there, and on my alpha position I have taken a halogen here. I treat it with excess of ammonia and I get falling product, which happens to be my isoleucine. This is very simple reaction to perform. Let us move on and talk about a third method, which is Gabriel Malonic ester synthesis method. Now, this method is slightly more involved. It is also called as amido malonate synthesis. This method actually is a combination of two methods, one of Gabriel synthesis of amines and malonic ester synthesis of carboxylic acids. Essentially, in this case, we are going to introduce both the groups here. In the previous two methods, we were just trying to introduce amino group in the alpha position of the carboxylic acid. Now, in this method, we are going to use a method in such a way that we introduce the amine as well as the carboxylic acid over there. Let us see how does it happen. But before we move further, probably it will be worthwhile to talk about, just recall what are these two methods here. Let us recall Gabriel method of amine synthesis. In this method, what we do is we take theriamide. Theriamide in presence of base like KOH gives me a theriamide anion here, and this theriamide anion can be treated with an alkyl halide here, and what you get is an N-alkyl product here, that is N-alkyl theriamide. So, that is my first step of this. And then in the second step, what we do is this alkyl derivative, I heat it with hydrazine. With hydrazine, what happens is I get a hydrazide here and my amine comes out of it. That means, amine comes out as a product. It is a very simple method of preparing primary amines. So, that is one method which we are going to integrate into our this synthesis. The second method we have to recall here is the malonic ester synthesis of carboxylic acids. In this method, what we do is we take malonic ester, that is my malonic ester here, and we alkylate it. We alkylate it on the carbon atom, which is alpha to both carbonyl groups here. That means, these are my two carbonyl groups here. So, this is my carbon here, which is alpha to that. So, I do alkylation. So, what I get is an alkylated malonic ester here. Then thereafter, I perform a hydrolysis here. As a consequence of hydrolysis followed by even decarboxylation, what I get is a substituted acetic acid here. So, this is my carboxylic acid which I can generate from here. Now, we can take up amido malonate synthesis of alpha amino acids. Now, this synthesis actually employs diethyl estamido malonate as the starting material to get the racemic alpha amino acids. The reactions are as follows. What basically we do is this starting material, that is diethyl estamido malonate here, we treat it with sodium ethoxide followed by the alkyl halide here. So, as a consequence, what happens is we get an alkyl substitution at position alpha to the two esters over there. There is two carbonyl groups over here. Thereafter, we undertake the hydrolysis part of it. When we do hydrolysis, two things happen here. One, we generate a carboxylic acid group here, as we just learnt earlier, and then secondly, this production here also gets hydrolyzed, and what you get is a free amino group there. So, this is a very clever synthesis which is used for generating alpha amino acids. The amino acid target it can be achieved by choosing a right kind of a Rx here, because this alkyl halide will determine what amino acid we are going to get as a product over there. Let us take an example. Now, suppose I want to synthesize phenylalanine. So, what do I do is I start with the same material here, sodium ethoxide here as before, then I choose benzyl bromide as my alkyl halide, because my side chain here happens to be CH2 PHE, that is the C6H5. So, if I want to use benzyl group as my side chain, so I use benzyl bromide as my the alkyl halide here. As a consequence, when this reaction takes place, I get the alkyl group over here, that is my target alkyl group which I want in my target amino acid. Then thereafter, the things are very simple, we just undertake the hydrolysis part of it. So, as before, we generate a carboxylic acid group and also get my amino group there, and then this is my side chain which I wanted to generate here. So, that is a very simple way of preparing alpha amino acids. Okay. Now, let us move on to yet another method that is called as stereosynthesis. In this method, basically amino acids are prepared from aldehydes in a two-step process. The first step is that we convert the aldehydes into an alpha amino nitrile. That is the following reaction: as you take an aldehyde, treat it with ammonium chloride and sodium cyanide, and what I get is an alpha amino nitrile here. This nitrile is then in the second step hydrolyzed to give the alpha amino acid as the product here, and here again I will be getting a racemic product here. The reaction is very simple, but again suppose I want to target a specific amino acid. So, that actually is achieved by using a suitable aldehyde group there, because the kind of aldehyde as a starting material which I use, that is going to determine what amino acid I am going to get as a target product over there. Suppose I start with acetaldehyde. So, this is my R group here. So, this CH3 will come out as my side chain here. So, I will be getting alanine as my product here. Reaction sequence is the same, that is I take acetaldehyde as my starting material, treat it with ammonia and HCN, I get the nitrile, and then I do the hydrolysis part of it. Reaction sequence is very simple, and this method is used very often to generate alpha amino acids. Now, all these methods what we have discussed so far, the general methods, these general or conventional methods, they all of them give us racemic mixtures. That means I will be getting product which will be D and L as a mixture of the two. Now, in principle this can be separated out. That means we can use the number of methods available to resolve this mixture to the individual components there, but these methods are very elaborate. There is a lot of processing involved in that, and secondly there is a loss of material, because suppose I get 50% of L, 50% of D, and I need only L, the 50% of D is gone waste. So, there is a lot of loss of material involved in that, and thirdly it is a time consuming process. So, what we need is, we desire that if we could prepare optically pure alpha amino acids, because our amino acids which I want to use for any kind of an application, I would want it to be optically pure, and that kind of synthesis is possible here, and the way out is that we try to use some methods which can give us enantiomer selective synthesis. That means I can do that by using some kind of a chiral catalyst there. The strategy is as follows: what we do is, we take an achiral alkene. There are a number of methods available there. I am just going to share with you only one of such methods there. The strategy in this method is that I start with an achiral alkene, do its hydrogenation in presence of a chiral agent. The reaction is as follows: this is my achiral alkene. I do hydrogenation and I use a chiral catalyst along. When I do that, the product I get here as a consequence of it is of a specific kind of configuration here. So, I will be getting an S product which I desire it to be. So, that is the basic strategy here, that is I am going to use a suitable chiral catalyst. The catalyst is going to determine what enantiomer I get as a product there. Now, let us take an example, say, of synthesis of phenylalanine. What do we do is, we take an achiral alkene as shown over here and do its hydrogenation, and along with in this process I use a chiral catalyst here. This chiral catalyst is very complicated one, which basically there are two components of this. One is a rhodium compound here, and second is that this component here, this is a phosphorus compound, which basically is called as BiNAP. It's a abbreviation of a long name here, but we will not get into the names and things like that. But for us, it suffices to know that we are using a chiral catalyst there. When I do that, so I will be getting the product as my S enantiomer here. That is, I am getting N-acetyl phenylalanine. That is, I am getting my target amino acid, but I am getting it as a N-acetyl derivative of that. But important is that I am getting an S enantiomer 100% enantiomer excess. That means there is no trace of the R enantiomer there. So, I am getting only the S enantiomer which I want here. Then the next step, I can do hydrolysis of this, and I can get my target amino acid which I want. So, that is the method available to us. This method is slightly expensive, but the important thing is I will be using a very small amount of catalysis required in this process. Now, it will be worthwhile to make a mention of Ryoji Noyori. he is the one who got Nobel Prize in 2001 for developing asymmetric hydrogenation reaction using chiral binap catalyst there. So, because he is the person who developed this catalyst, and whereby we can do asymmetric hydrogenation and get the desired product in suitable enantiomeric excesses there. Okay. Now, having talked about different methods, the general methods and enantioselective methods of synthesizing alpha amino acids, now let us move on to talking about the reactions of alpha amino acids. And as I mentioned in the beginning, because alpha amino acids, as we will recall, that they have got two kind of functionalities. That is, it has got an acidic functionality, also got a basic functionality, there is an amino group there, and accordingly it shows properties of acids as well as that of bases, and also some kind of properties which are based on both the functional groups over there. And there are a number of reactions possible there, and what we do is we will try to talk about only the important reactions of alpha amino acids, and here again I will talk about two categories of reactions. The first category is the ones which are important for determination of alpha amino acids, and second are the ones which are important for synthesizing peptides, which we will be taking up in the next session. Okay. Now, let us continue with reactions which are important for determination of alpha amino acids. In this category, the first reaction we will take up is the reaction with nitrous acid. The reaction is very simple here. So, what we do is we take alpha amino acid, treat it with nitrous acid, and what I get is I get a alpha hydroxy compound here, and nitrogen comes off here. Now, this is a typical reaction of primary aliphatic amino group, and the importance of this is that in this reaction this nitrogen comes out through formation of a diazonium salt here. This is a basic school chemistry, and important thing in this whole process is that this nitrogen which is coming out quantitatively, and this nitrogen can be estimated, and that forms the basis of Fans-like determination of amino acids containing primary amino group. So, it means wherever there is a primary amino group in an amino acid, that can be determined in this particular way, and this is one method which is used for, it is a very old classical method of determining the amounts of alpha amino acids. So, that is one reaction, very simple and useful reaction. The second reaction is the reaction with formaldehyde. In case of formaldehyde, what happens is the formaldehyde undergoes nucleophilic addition to our amino acid, and what I get is a reaction, a product of this kind. Say I take glycine, react with formaldehyde here, I get series of number of products over there. The importance of these products is that this basically the formaldehyde actually kind of blocks, derivatizes the amino part of the amino acid here, and what you get is, so we will see that this amino group here, and in this case also, both the cases it is blocked here. So, the amino group of the product is blocked and the COH group is free. So, what we can do is you take an amino acid, treat with formaldehyde, block the amino group, and the free carboxylic group can be titrated with the standard alkali. When you do that titration, I can determine the amount of COH group, which in turn gives me a measure of the amount of the amino acid here. So, this forms the basis of Sorensen's 4-mole titration, because that's the name given to that, because this titration which was suggested by Sorensen way back about 100 years back, this makes use of this particular reaction, that is we block the nitrogen part of it and titrate the carboxylic group acid, carboxylic acid group to determine the amino acid there. That is my second method. The third one, reaction with ninhydrin. This is one of the most crucial one, the reaction which amino acids undergo. This actually is a two-step reaction. In the first step, there is an oxidation taking place. What happens is ninhydrin reacts with amino acid, and this gets reduced to the following form, and the amino acid gets oxidized to amino acid. That is my first step here. In the second step, what happens is this amino acid what I get in the first step undergoes deamination. In the process of deamination, this generates a molecule of ammonia. But what is important for us is the generation of ammonia. This ammonia which comes out as a consequence of this reaction, the reaction put together will be oxidative deamination, and this ammonia which is coming out that actually reacts with hydrogen dentane, which actually is formed again from ninhydrin. We will see how does it happen. And the overall two-step reaction which we have just seen here is called as oxidative deamination. First step is oxidation, second step is deamination, and the product of this is generation of ammonia. Let us see how does the formation of hydrogen dentane take place. What happens is that the ninhydrin which got reduced in the first step, that reacts with another molecule of ninhydrin as follows to give us the product here, that is hydrogen dentane. This product is obtained by reacting the ninhydrin with the reduced molecule of ninhydrin. The two put together give us this product here. And the ammonia which came out as a consequence of oxidative deamination, that reacts with hydrogen dentane as follows. And in this case, what you get is this is the following product coming there, which in the presence of acid we can get this species here, which gives us very intense violet coloration, and that is this reaction forms the basis of identification of amino acid in wide spectrum of applications there. Most importantly, we used it for detection of amino acids in any kind of chromatographic separation, whether it is a paper chromatography, column chromatography, or any kind of chromatography we do. We use ninhydrin as a means of looking for or identifying amino acids present there, because this is a very characteristic and useful reaction of amino acids. This reaction is so very useful that it can be even used for developing latent fingerprints here. This is one of the most commonly used kind of a reagent to develop the latent fingerprints. What basically happens is that in case you touch any place there, the sweat contains large number of organic compounds, and some of them happen to be amino acids. It is this small component of amino acids which is present in the sweat which forms a mark somewhere. So, that is what is exploited in this particular method. That means, wherever you suspect a fingerprint to be there, we spray it with ninhydrin, we develop this kind of a impression of the fingerprints there. So, that is one application of this very reaction of ninhydrin, whereby the ninhydrin reacts with amino acids to give you characteristic colors there. Let us move further on. These are the two the reactions now we talked about. Basically, they were about the ones which can be used for identification. Now we move on to the reactions which are used for synthesizing peptides, because they are the ones which are useful for synthesis of peptides. Let us see what they are. The first reaction is acylation of amino group. This is very, very important here. What happens is, in this reaction, the amino group of the alpha amino acid is acylated in it can be done with a number of reagents there, simplest being acetic anhydride. This is one of the simple reactions there. That means, you have an amino acid, say glycine, I treat it with acetic anhydride. So, what happens is this acetic anhydride kind of derivatizes this and nitrogen part of it, that is the amino part of it. What I get is a N-acyl glycine. This is a very important reaction there, because effectively what it does is it blocks the nitrogen part, that is the amino group of the amino acid. And this is very important, because we will be learning about it in the future sessions here. That is, in case of peptide synthesis, it is very crucial that if we want to combine two amino acids to make a peptide, for one of the amino acids the nitrogen group should be blocked, for the other one the COH should be blocked, then only the other two reactants, other two groups will be reacting together. We will talk about it later on. But it is important for now, it is important for us to know that this blocking of nitrogen, this amino group is very, very useful or important for any peptide synthesis to be undertaken, and this particular reaction helps in that. So, another significance of this particular reaction is that once I do acylation, I will be getting an N-acylated product here, that means this is a carboxylic acid. The advantage of this particular reaction is that this can be even further kind of activated, because a carboxylic acid group will not be very effective or very reactive for kind of peptide synthesis to be taken up. That means the kind of condensation reaction will not be very effective. So, it will be advisable to activate this carboxylic acid group, and that can be done by converting it into an acid chloride, and that can be done with the help of thionyl chloride here. So, what I get is this is my N protection here, and then this gets activated in form of a acid chloride. And actually if I want to just do direct activation, it is not possible because this nitrogen, this amino group interferes in that. So, first we block the nitrogen part of it, then we activate the carboxylic acid part of it. So, that is the importance of this particular reaction, which is very, very useful in our peptide synthesis. The second important reaction for this in this particular perspective is that is esterification of carboxylic acid. I just mentioned that in case of peptide synthesis, we need to block for one of the amino acids, we need to block the nitrogen part of it, for other one I have to block the carboxylic acid part of it. So, this reaction I am going to talk to you about, that is esterification of carboxylic group, that actually serves the second purpose. That means, amino acids can be esterified by treating with excess of an alcohol and a catalyst. What happens is as follows. Suppose I take alanine, this is my simple amino acid, I treat it with HCl in presence of alcohol. Alcohol is my reactant here, HCl is a catalyst here. So, in this reaction what happens is I will be getting an methyl ester of the amino acid here. So, by generating or by creating a ester group over here, I am blocking this COH group, and then my NH3 is free to participate in the peptide synthesis part of it. Another beauty of this particular reaction is that just by simple hydrolysis I can generate back my amino acid. That means, I protect it, perform the condensation reaction, generate my peptide bond, and then thereafter I hydrolyze this group. So, I get my free acid back. So, this reaction again is very, very important for peptide synthesis. Let us sum up what we have done today. Today actually we have taken up two very important aspects of the chemistry of alpha amino acids. First one was the chemical synthesis of alpha amino acids, and in this context we talked about some general methods of synthesizing alpha amino acids. We talked about 4 such methods which are the most important ones nowadays, and we realized that the general methods give us racemic products, and we kind of argued for the need for methods which can give us optically pure products there, and in that context we talked about enantiomer selective method there. We talked about one such method over there. Thereafter we took up the reactions of alpha amino acids. Here again we talked about 2 sets of reactions. The first set belonged to the reactions which were important for the identification of alpha amino acids, then hydrogen reaction and many more were talked about, and the second category was the reactions which were useful for peptide synthesis, about which we will be talking about at a later stage.